All right, this is a really interesting problem, and it seems like it introduces something that is pretty deep in algebra, I want to say. Like, I feel like this isn't an uncommon thing, or at least I seem to think that I've heard of this being referred to before, like from a more higher level perspective. But whatever, it's a neat problem, so let's just get to it. We gotta prove that this is a group. So we know that G is a group, so so G contains an element in identity 1. So let's define an element 1 in GS to be the map. I just recognized the song that's playing outside, and with the people on construction, it's Sublime's version of Summertime. But anyways, 1 in S be the map. Since I kind of prefer the original. I seem to remember like Coltrane or something having like a really good version of it. Anyways, all elements of S. So 1 in S sends everything to 1. Then for all F in GS, and for all S in S, 1F at S is equal to 1S times Fs, which, let's see here, 1 of S is, sends everything to 1, so it's just 1 of F, which is F of S. And of course, going the other way, so 1 as an element of GS is the identity. Next, I'm going to let F and G be in G to the S. We want to prove closure under multiplication. For all S and S, F and S and G of S are clearly in G because they're in G to the S, so they send elements to G. So, multiply them together, Fs, Gs, and G. So, Fg maps S into G, so Fg is in GS. So if F is in GS, the last thing is if F is in GS, find G from S to G such that for all S in S, G of S is, now F of S is an element of G, so it has an inverse in G. Then obviously G is in G of S because it maps S into G. And for all S in S, Fg of S equals Fs GS. So that's just Fs inverse equals 1. That's Fs inverse Fs, which is GS Fs, which is GFS. So the inverse of S is G, which is in G to the S. So hence, G to the S is a group. And we're done, except for the fact that we are not done. Now let H act on G to the S by here. So HF of S equals F of H inverse S, where little s is in big S. So I claim this defines an action of H on G to the S. So how do we prove that? We must prove for all F and GS that 1F equals F, and if you give any H1, H2, and H1, H2 of F equals H1, H2 of F. This is what it means to have a thing act on a group, or a group act on a set. So, yeah, that's just the definition, and so let's get to it. So 1 is clearly an H because H is, what is H? H is a transformation group. So H is a group, and groups contain 1. And so 1 is definitely an H. And for all F and GS, 1F, the function evaluated at S is F of 1 inverse S, which is Fs. So, and that's of course for all little s and big S. I'm just not going to write that all the time because I don't feel like it. Okay, so 1F equals F, so that's good. Next, let H1 and H2 be an H. Then for all S and S. Is this another place where I can drop it? Yeah, sure. So now here we have to be a little careful with the parentheses and what things are doing. I know I got confused about this when I was doing it the first time. So H1, H2 of F, this is a function, and it sends S to S. No, S to G. So this is going to take S as an input. But let's see, what is this equal to? We know by the definition of this product here is H1, H2 acting on F. And that is defined as F of H1, H2 inverse of S. And I've just put the S in here because we're going to plug the S into the H1, H2 inverse and then into F. And so what is this equal to? We look at the inside, and H1, H2, this is just normal composition of functions. And so this is F of H2 inverse of H1 inverse of S. Okay? But then what is this? Now we kind of take this composition, F of H2 inverse, and we convert it to H2 acting on F. So this is H2 acting on F, evaluated at the element H1 inverse S. Here. And then what is this? Then we convert this again to H1 acting on H2F, this whole thing being evaluated at S. And so thus, H1 H2F equals H1 of H2F. So yeah, here you have to be really tricky about, because you use, I guess the main trickiness here is that when we're doing composition of functions, we just write A composed with B as a B. So we just don't do anything in here. And we're also doing H acting on F, we're writing that as HF. And so there's a lot of sort of ambiguity here between when you like do just two things next to each other, whether you're doing composition or you're doing an action. And you have to work through that. I guess if you wanted to be really pedantic, you could have different symbols for each and write them out. That might be easier if you're having trouble kind of parsing this together in your head. But at least for this I don't think it's really necessary at this point, because I think this kind of shows you how it all works. And usually you can see by context what is being used. Although I guess technically when you do the H, if you do like acting on F, I think I've seen this before, is H inverse F or whatever. How does it work? H acts on F by F composed with H inverse. So when you act on, you are converting to composition. So I don't know. It might be easier for you to do it that way, but it might not. Whatever works for you. So hence, we have defined an action of H on GS. And there we go. This completes our proof.